All right, so in class we looked at a couple of different light bulbs that were, made up of different elements giving off light. And as that light passes through the spectrometer, we can see that that prism within that spectrometer breaks it up into its different components. So the red light, it gets deflected the least, and so it shows up in the spectrophotometer, or the spectrometer, pardon me, way down here at this end of the spectrum. And then the purple and the blue get deflected more. You can see the angle that they're getting deflected at there. So they're going to wind up way down here at these shorter wavelengths. And we'll talk about what wavelength means shortly. But longer wavelength, like red or orange light, are less deflected as they pass through the spectrum. That's how a rainbow is created, for example. So, water drops in the air deflect blue and purple more than they do red and orange, and so it separates the color of light coming from the sun into its components. So, as we're looking at electromagnetic radiation, we have to understand some things about the nature of a wave. So waves can be long, like radio waves or microwaves. They can be short, like X-rays and gamma rays. These ones in between, like visible light, are actually just the right size for us to see, to actually perceive with our eyes and with our brains. And that's basically just an adaptation that we have developed over the years so that we can pick things out in nature, whether it's food or predators coming at us or whatever the case may be. But visible light just means it is radiation of a certain wavelength that we're able to see. Okay, so I've used the term wavelength a couple times. We should probably define it. Wavelength is the distance from crest to crest of two consecutive waves. So if I try to kind of draw a wave here, a wave, it might look kind of like this, several waves in a row. And so a wavelength is just the distance from here to here. So two identical spots on consecutive waves. And the symbol actually is this weird Greek symbol. It looks like an upside down Y. It's called a lambda, but basically that stands for wavelength. And wavelength is a length, so it's measured in meters. So things like visible light might have a relatively, short wavelength, whereas radio waves would have very long wavelengths, so big distances in between crests, okay? And that brings us to frequency. So we also have frequency, which is another thing we can measure about a wave. It's the number of waves to pass a point per second. And so if you can imagine these waves are moving, the closer the waves are to each other, the more of them will pass a point per second. And the longer the wave is, like if you have a really long wave, you're going to have very few waves pass per second compared to this short wave here. So frequency is just the number of waves that pass a point per second. The unit is either 1 over s, or one like in other words, waves per second, or sometimes it gets Hz, which stands for hertz. So if you've ever heard of frequencies for like a Wi-Fi transmitter, might be given in like megahertz or something like that. That's what that's referring to. It's just the frequency of the radio waves that are being sent out by that little transmitter. So the symbol for frequency is also a Greek letter. It looks just like a V, but it's technically a Greek letter nu. But you don't really have to know the name of it. Just know that that symbol means frequency and know what frequency means. Then next up we have energy. So energy of waves tends to be greatest where wavelength is shortest. So if you look at the three waves I've drawn up here at the top, this middle one would be the one that we would expect to have the most energy. In other words, it corresponds to an electron within the atom falling the biggest distance, whereas these long waves are lower energy, and those might be given off if an electron is not falling a very big distance. The symbol for energy is just capital E. And then finally we have speed. Now the interesting thing about speed is that all radiation, visible light, radio waves, microwaves, X-rays, they all travel at the same speed. The symbol is C, And the value is this number, 3 times 10 to the 8th meters per second. So very, very fast. Okay, and then we've already talked about the fact that wavelength and frequency, the longer the wavelength, the fewer waves pass a point per second, which is frequency. So that means that those two are inversely related. And then we can use the equation, or an equation, I should say. And that equation basically says that the speed of light is constant, so that's c, and that it is equal to the product of wavelength times frequency. And this shows an inverse relationship, because if we're always going to get the same answer for c, 3 times 10 to the 8th, right, meters per second, then that means that as wavelength goes up and gets longer, the frequency would have to go down, otherwise we wouldn't get a constant answer. And so this is a good equation to have, and you'll always be given this equation. You don't have to memorize it or anything, along with the speed of light, the value for the speed of light. So it's a good equation to have because it allows us to solve for an unknown wavelength or frequency. So if we take a look here at this question, what is the wavelength of electromagnetic radiation, which just basically means light, but it could be, outside of the visible spectrum too. It could be X-rays or something. But it says it has a frequency of 3.05 times 10 to the 16th 1/seconds, and that just means waves per second, right? So if we look at our original equation that we just wrote, so C equals wavelength times frequency, then we just rearrange it to solve for wavelength, right? It's asking us to solve for wavelength. So since wavelength is currently being multiplied by frequency, we simply want to divide both sides by frequency. And that is going to get wavelength all by itself, right? So essentially we just want to plug in the speed of light divided by the frequency that the problem gave us, right? So on top, I'm going to say the speed of light is 3.0 times 10 to the 8th meters per second. Right, that's my speed of light. And then on the bottom, I put in my number 3.05 times 10 to the 16th 1/seconds. And I know I've done this right if everything cancels properly. And if I'm looking for wavelength, right, which I am, I should end up with meters as my unit, which I will, because seconds will cancel. Oops, I wrote 1/2 instead of 1/seconds. So seconds will cancel and I'll end up with meters in my answer. So then we just get out a calculator. And I got 9, let's see, I want 3 sig figs, so I'm going to get 9.84 times, 9.84, and this is going to be a very small number, so times 10 to the -9, and that would be meters, right? Because we said seconds would cancel, and so that is an example of finding wavelength from frequency. Okay, so let's take a look at an example question, or another example here. If I have a wavelength of 625 nanometers, right? The first thing I'm going to do is recognize what I'm looking for, which is frequency. And so I'm going to take my original equation, C equals wavelength times frequency, and I'm going to rearrange it to get frequency, right? Which is this guy. So we have to divide both sides by wavelength. And so what you'll notice pretty quickly is every time, I'm showing the algebra here that we're doing, the canceling, but every time we're going to end up with, when we're looking for one variable, it's just going to be the speed of light divided by the other variable. So it becomes pretty simple. It's always the speed of light on top. Now, for this problem, I can go ahead and put the speed of light on top, and that's 3 times 10 to the 8th meters per second, right? That number never changes. But for this problem, I was given a wavelength in nanometers. So we're going to have to remember something about converting from nanometers to meters. So this becomes a conversion, 625 nanometers, nm. Just put that over 1. And then we try to get rid of nanometers and take it to meters. And the reason we have to take it to meters is because our speed is given in meters per second, not nanometers per second, right? So 1 meter is larger, and this bottom number is going to be 10 to the 9th. And again, I just got that by a little Gumuku chart, or just understanding the relationship between, meters and nanometers. And so this comes out to, if we get out the calculator, I'm dividing by 10 to the 9th, so it's 6.25 times 10 to the minus 7, which makes sense. It should be a very small number because we're dividing by a billion, basically. And so that's my number of meters. And so I'm going to put that in the bottom. That's going to go right down here. And then I'm going to get out the calculator. So 3.0 times 10 to the 8th divided by 6.25 times 10 to the negative 7. And we get 4.8. And I'll keep my 3 sig figs. So I'm going to throw a 0 on the end there. 4.80 times 10 to the 14th. Now the units are kind of weird on this because meters cancels, right? I had meters here and I had meters down here. So it is actually 1 over seconds is my unit. That also will sometimes be referred to as hertz. It's just named for a scientist that discovered some stuff in physics, and so he got a unit named after him. But there's our answer: 4.80 times 10 to the 14th, 1 over seconds, or you can say hertz. Okay, and then the other quality of light we have to talk about is energy. So the energy of light or radiation is related to wavelength inversely. So if you look at what's happening here, a lot of energy is being released as an electron maybe falls way down this great distance, and you notice the wavelength on this wave is very small. So over here, though, when the electron is falling a small distance, the wavelength is long, and that's because wavelength and energy are inversely related, meaning as energy goes up, wavelength goes down, and vice versa. Now, since we already know that wavelength and frequency are inversely related, well, then if energy and wavelength are inversely related, that means that energy and frequency are directly related. So as frequency goes up, energy is going to go up also. And that is given to us in the equation energy equals H times frequency. And so energy symbolized by E equals H. H is also known as Planck's constant. It's a very small number, 6.626 times 10 to the negative 34 joules times seconds. And I know that's kind of a weird unit, but just remember that Planck's constant isn't really directly measuring anything. Like the speed of light is actually how fast light is moving. This is just a constant that essentially makes the equation true, so that energy is directly related to frequency. So let's take a look at an example. How much energy does light have if its frequency is 5.20 times 10 to the 13th hertz? And so all we have to do is set up our equation. E equals H times nu, or frequency. But we don't really have to do anything to the equation because it's already set up to solve for energy. So we're just going to say E equals, and then Planck's constant is a constant. Again, you don't have to memorize constants. You'll get this given to you on your next test. So we just fill it in. 6.626 times 10 to the negative 34 joules times seconds is our unit. And then the frequency is 5.20 times 10 to the 13th. And I could write hertz, but really in terms of canceling units, it's going to make more sense to use the other alternative there, which is 1/seconds. And then we just punch it in the calculator, right? And we get 3.4. I'm going to keep 3 sig figs just like my frequency. 3.45. 3.45 times 10 to the -20. And if you'll notice, seconds will cancel, and that will leave me with joules, which is the proper unit for energy. And I know you have one more problem in your notes, but we'll go ahead and save that one for class. So that is all for today.